Good afternoon, dear friends. Today we are starting the chapter 9 at our textbook by Chang and Wainwright. The chapter 9 is on optimization. In the American English, it is written with Z, optimization or optimization. And in the British English or French, it is written with S, optimization. In French, optimisation. And in Turkish, we use also optimization with the Turkish pronunciation, but we can say also en iyileme or en iyileme. So this is optimization. Today, our topic is optimization. So, from now on, we will not be studying an equilibrium occurring by itself, like we did in the previous models, but now we'll start studying an equilibrium that the actors, players, whatever the decision makers, they try to achieve, to get involved as their objective. So they have an objective, they have an aim now. Or if we make the optimization, we have an aim. We want to reach the maximum value of some good thing or the minimum value of some bad thing for us. This is the difference from our previous chapters, from our previous models. So we are starting the engineering. In fact, an engineer does exactly this. It tries to produce something with the minimum, with the least cost, the minimum cost, or engineer or a manager tries to obtain a goal, sort of profit, for instance, maximize its profit to achieve the maximum profit out of something, out of an activity. So this is what we will try to do now, what we'll learn to do now. All right. First, let's start with some terminology. Here we will learn the necessary terminology in Latin, English, Turkish, and French, because all we use in several contexts, in the different contexts, and most of the terminology is common, but they are pronounced in each language according to this language's pronunciation. So the first word is extremum. Extremum in Latin, extremum in English, and extremum in French, and we can say in Turkish, uç değer. It's an extreme value. And the plural of it is not extremums, it is extrema, because this is a Latin word, and to the English it passes directly from Latin, and its plural is extrema, not extremums. An educated Englishman or British person would call extremum extrema. The singular is extremum, the plural is extrema. So you should learn it as well. This means extreme value, uç değer in Turkish. Then we have optimum. The plural is optima. All these terms are Latin. And they are pronounced in English with the English pronunciation, but the English in the English language, one uses the original Latin word, pronounces it in the English version, in the English pronunciation. In French and in Turkish, we pronounce it a little bit differently with French or Turkish pronunciation. And we have also Turkish words for them. Optimum, the plural is optima, means the best in English. And in Turkish, en iyi. In French, it is pronounced optimum. And optima. The fact or the action of it is optimization or optimization. In French, optimisation. And in English, it is optimization or optimization. In American English with Z, in English, in British English with S. The difference is this. And in Turkish, the exact Turkish word for it is en iyileme. We have also maximum, maxima in plural, maximum in singular, which means the most, the greatest. in Turkish en çok, en büyük. In French, and we also use the term maximum in Turkish, or minimum, the opposite of it. In French, it is written the same as in English. It's pronounced maximum. Then we have also the opposite of it, which is minimum, minima. And the fact or the action of maximum, the maximum is maximization or maximization. In Turkish, it is en çoklama. In French, maximisation. And it can be pronounced in English maximization or maximization. Minimum, minima in plural, minimum in singular. It means en az, en küçük in Turkish. Minimum in French. Also in Turkish, we use minimum with the Turkish pronunciation. We just take these words rather from French. So our pronunciation is similar, it's very near to the French pronunciation. Then the action of it is minimization or minimization. In Turkish, en azlama. In French, minimization. Minimization in English, and in Turkish it is en azlama. In French, it's minimization. So you see, and in Turkish we can say minimization or minimum. Well, we don't say minimization very much, but we use maximum, minimum in Turkish as well. Optimum as well, sometimes. So this is for the terminology. So 9.1, the first topic is optima and extrema. So the best values and the extreme values. You know, there are extreme sports. When we say extreme sports, we mean those sports which are difficult to perform. Very sort of high skilled and highly trained people can do these sports, like these jumping with paraglides and all this stuff, the bungee jumping and all these difficult sports. Those are called extreme sports. So extrema, you see, it's really so difficult to achieve. It is the uppermost or lowermost or whatever the outermost value. It is always most, you see. So what is optima and extrema? What is optimization? So we are looking for the extrema, for the extreme values of our objective function. To choose the best path in order to achieve an objective. This is the definition. To choose the best path, best way, path, a path is a way, to choose the best path in order to achieve an objective, a goal. So we have a goal, we want to achieve it with the best way, with the best, going from the best path. So what is the objective? It is the objective function. Y equals f of x, for instance, one sort of univariate objective function. Y equals f of x, a primitive function. This is our objective function. We want to maximize or minimize it. If it is something good for us, we want to maximize it to obtain the uppermost, the greatest value. If it is something bad for us, like a cost, for instance, then we try to minimize it to achieve the least value, the smallest value of it. X is our choice, control, or policy variable. This is we can say it's it's like an exogenous variable. Y is the endogenous variable, our objective value, our objective function. And X is one of these independent or explanatory variables which we use to maximize or minimize this function, this objective function. And it is called choice variable or control variable or policy variable. Well, in economics we call it more choice variable. Engineers call it more control variable, and in all social sciences, especially political science and so on, it is used as policy. It's called as policy variable. But you can use both these terms. You can use any of these terms: choice variable or control variable or policy variable. So a typical optimization problem is written like this: max y equals f of x and sub x. You might make an x, you put an x under the max. Meaning we maximize, we achieve to find the uppermost value of y equals f of x, our objective function, by using the x. Our control variable is x. This means this. This is the summary way of writing an optimization problem. Example. Let's see an example. Pi, the Greek pi letter, is profit. It is the initial of profit, P, but P we use for price, so we use pi, the letter pi, the uppercase letter pi, Greek letter, for profit. So we will maximize our profit. Profit is something good for a firm, for a company. So a company, a firm, tries to maximize its profit by using the quantity produced or sold, Q. This is a typical economic optimization problem, a maximization problem indeed. If it were cost, then we would minimize it. So, what is profit? The profit is total revenue minus total cost. And both total revenue and total costs are functions of the quantity produced, Q. So, pi is total revenue minus total cost. We will maximize, we will find the uppermost value, the greatest value of this difference by using the quantity produced Q. TRQ minus TCQ, or it can be written RQ minus CQ for total revenue and total cost. The difference is the profit. Profit is the objective function. Q is the choice variable. You see? All right. Then. 9.2 is relative maxima and minima, first derivative test. So how shall we find these maxima and minima and other critical points, other interesting points, and how shall we know which one is maximum, which one is minimum, and which one is inflection point? There is also another critical point and another interesting point, kind of interesting point, which is called inflection point. So also about maxima and minima, we can speak of absolute maxima and minima and relative maxima and minima, or absolute or global maxima and minima in a function, and relative or local maxima and minima in a function. To understand better, just look at this picture, this figure. It is from the notes of Wainwright at chapter 9, article PDF. There are these articles, PDF articles by Wainwright as lecture notes to our book, but you can also find it in our book, I guess. I just took it from this PDF file. So we have the point A. Let's assume that the domain of definition of this function is so much. It starts from A and it ends at H. It doesn't continue more. We will analyze this part of the function. So in this domain, from this X to the last one, which corresponds to H, the lowermost point of this function is A. There is no point lower than this. And uppermost point of this function is H. There is no point upper than H. Those are the absolute or global extrema. A is the absolute minimum, global minimum. H is the absolute or global maximum of this function. And we are not interested in them. There are techniques to find these absolute maxima and minima, but they are more elaborate techniques, and they are not the ones we will learn in this course. In higher courses, as optimization techniques, the discrete optimization or other kinds of grid search or genetic algorithms, you can find these points as well. But the methods we will learn in this course will find the relative or local extrema, meaning local top of hills and bottom of valleys, like this. B and E here are local maxima. C and G are local minima, and D and F are inflection points where they are like small balconies. This function changes its curvature then. All right, we will see. So A is absolute or global minimum. C and G are relative or local minima. A is lower than them. But C and G are local sort of bottom of valleys. Here we have valleys, and then there are bottom of these valleys are C and D. We have two valleys, two bottoms, you see. And we have two hills and two top of hills, B and E. Those are local or relative maxima, B and E, top of hills. So, and D and F, which are small balconies, neither tops nor bottoms, those are inflection points, and we will learn what they are and how to see them, how to analyze them. If we have a function, if we have a constant function like this one, y equals fx equals k, this one, both points, all points of this function, if y equals k, y equals fx equals k, all the points of this function are both absolute maxima and absolute and relative maxima and minima. A constant function has no minimum or maximum, or all of his points, all the points in a constant function are both relative and absolute maxima and minima. So this is for the constant function, and it's not interesting for us. In the second picture here, B, in the second graph, there is only a global or absolute minimum, and this function has no maximum. It goes on up to plus infinity. But here, at the 0, x equals 0, there is a minimum, which is a global or absolute minimum. It has no relative or local maxima or minima. We are more interested in this kind of graph, in this kind of function, the C, the third one. Here, it makes hills and valleys. So we are interested in finding these local top of hills and bottom of valleys. So local maxima and minima, or relative maxima and minima. E is a local maxima, a maximum. F is a local minimum. Relative maximum, relative minimum. We are interested in finding these indeed in this course. All right. So the first order necessary condition for relative maxima and minima. First order condition. It can be shortened in this way, FOC or first OC. It means first order condition. In order not to write long or every time, we can use these short forms. So this is a necessary but not sufficient condition. What for? For finding the relative maxima and minima, relative tops and bottoms of valley, bottoms of valley, tops of hills and bottoms of valleys, relative maxima and minima. It shows us the candidate points for relative maxima and minima. It doesn't tell us which one is which one. It just gives us the candidate points for relative maxima and minima. That's why it's a necessary condition but not sufficient. First order condition for relative maxima and minima. Necessary but not sufficient. Just just note it very well. Great. So y equals fx is our objective function now. We take its first derivative and equate it to 0. If at some point the first derivative of their function is equal to 0, this point x0, fx0, x0 is the abscissa, fx0 is the ordinate, so the two coordinates make the point. This point being a stationary critical point. What does it mean? The first derivative is 0. This is a stationary or critical point. Why? Because when the first derivative is 0, the movement on this function stops for a moment, for an instant. because the derivative is the instantaneous rate of change. So it means the function doesn't change at that point. It stops there. The movement stops there for just an instant. And then it continues, of course. So such kind of points where the first derivative is 0 are called stationary or critical points. Great. If the function has a relative or local extremum at x is x equals x0. So the first derivative being 0 is a necessary but not sufficient condition. It's a first order condition. It shows us at which points the movement of the function stops for a moment, and the tangent line to the function becomes parallel to the x line, to the x-axis, x-axis, the horizontal line. The tangent line to the function at that point becomes horizontal. Those are the points where f prime, the first derivative, is equal to 0. That means there is a candidate for a local minimum or maximum, but we don't know which one is which, and there, it can be also an inflection point. So, first, for the critical points, for the candidates or of extrema and extrema, minima and maxima, we can have two things. Either the first derivative is 0, like these points, C and D, in the figure here in the figure B, smooth functions, or smooth function with smooth parts. So we have smooth valleys and smooth hills. Then we will see that at the bottom of the valley or at the top of the hill, at the local minimum and maximum, the first derivative is 0. The tangent line of the function at x0 will be parallel to the horizontal line, x-axis, as we see in figure B here. Or there is another possibility as well. F prime x0 may not exist at all. The function is broken and it makes a sharp corner at the top of the hill or at the bottom of the valley. We can have some sharp sort of maxima and minima. Then, as we know from the chapter 7 or chapter 6 and 7, in such cases, when there are sharp corners, the derivative from the left and derivative from the right are different, so there is no derivative at this point. These at A and B, this function has no derivatives. It is continuous, but at the points A and B, the function has no derivative. Against C and D, at C and D, it has a derivative. The derivative is 0. You see, we can have two different cases. But in both cases, whether the first derivative is 0 at that point, or that it doesn't exist at all, but the function being continuous. It is defined here, determined here, continuous, but the derivative does not exist because at these sharp corners, the derivative from the left and from the right are different. The slope from the left and slope from the right are different, so the derivative doesn't exist. So either of them show us or give us candidates for local minima and maxima. Local maxima and minima, you see. So those are the cases we can have for the first order condition. But the first order condition gives us only candidates. It doesn't say us what they are. They don't. It doesn't say us tell us whether those are well, bottoms of valleys or tops of hills, whether they are minima or maxima. So we have to have another test for this. So the first sufficient condition, which is, note that very well, attention, sufficient condition is a second order condition, although here it uses the first derivative. That the first derivative is equal to 0 or it doesn't exist is a first order condition, necessary condition. Now we are coming to another condition, which is a second order condition, which is a sufficient condition for determining which point is maximum, which point is minimum, or which point is inflection point. And this is called first derivative test for relative maxima and minima, for relative extrema. Although it uses the first derivative, this test, it is a second order sufficient condition. I underline it. All right. So, at x equals x0, at this point, if f prime x0 is 0, it's a stationary point, it's a candidate. So the movement stops for an instant, for a moment, and the tangent line to the function at x0 is parallel to the x-axis, to the horizontal line. Great. This fact that the first derivative is 0 gives us only the candidate. It doesn't say what it is. So how shall we know? This is necessary condition, first order necessary condition. The second order sufficient condition with the first derivative is, it goes on like this. And why and? Because we need both conditions, both the first order condition and the second order condition. So after the first order condition is fulfilled, we check the second order condition with the first derivative here. There is also another one with second derivative we will learn. All right. For x less than x0, I mean if x for x less than x0, f prime x is greater than 0, which means the function is increasing. The function is going up. If f prime x, the first derivative, is greater than 0, it means the function is climbing, the function is increasing, it is going up. If for x less than x0. Then for x greater than x0, the first derivative is negative. It means we first go up, then come down this very point, x0. For x less than x0, f prime x is greater than 0. So the function goes up, it is increasing. For x greater than x0, when we pass to the other side of the x0, when x is greater than x0, f prime x is less than 0, meaning that the function is decreasing then, which we go down. So if we go first up, then go down, it means this is a top of a hill. We could have been blind people. We could still understand that we are on top of a hill. How do you do it? If we first climb and then go down, if we first go up then go down, it is the top of a hill. So we don't need to see it. So this is the test, the first derivative test, which is a second order condition, sufficient condition for local maxima and minima and inflection points. So x0 fx0 is a relative local maximum, top of a hill. Indeed, one goes up a hill first and then goes down from there. The first derivative is before that point, it is positive. After that point, it's negative. We go up and down then. So it is the top of a hill. It is a local maximum or relative maximum. If, on the contrary, at x equals x0 at this very point, f prime of x0 is 0. At the very point, the first derivative is 0. The movement stops for a moment, for an instant. And for x less than x0, f prime x is negative. And for x greater than x0, f prime x is positive. It means we first descend, we first go down, and then ascend, go up. If we at the very point, it's a kind of flat. We just stay there. The tangent line is parallel to the x-axis, to the horizontal line. It's horizontal. So it means we first go down and go up afterwards. F prime x is negative. The first derivative is negative before the point x0, and after the point x0, it becomes positive. So we first go down and then go up. So this is the top of a. This is the bottom of a valley. This is a relative or local minimum. You see, it is sufficient to know it. Even if we were blind people, we could have felt it. So x0 fx0 is a relative local minimum, bottom of a valley, One goes down the bottom first, then goes up from there, exactly. But yet, there is a third case. At x equals x0, if f prime x is 0, which can be as well. At an inflection point, it can be 0 as well, the first derivative. It is not necessary. It can be also different from 0. The particularity of an inflection point is not that its first derivative is 0, its second derivative would be 0 there, as we will learn. But the first derivative can be 0 by chance as well at an inflection point. It means you have a small balcony over there. The movement stops for a moment, for an instant. The tangent line to this point, to the curve at this point at x0 becomes horizontal, all right? And for x less than x0, f prime x is less than 0, and for x greater than x0, f prime x is less than 0 again. Which means you are going down, you come to this point, you just stay for a while, for one moment, and you are continuing to go down. In contrast to a top of a hill or bottom of a valley. To the top, you first climb, you first go up, then down. In a bottom of a valley, you first go down and then up. But in at an inflection point, you go up and continue going up afterwards. Or you go down and continue going down afterwards. So at both parts of both sides of this inflection point, the derivative of the function has the same sign. If you go up, you continue going up. It is positive. If you go down, you continue going down. It is negative. So it is a small balcony. x0, fx0 is an inflection. Then, if it is so, x0, fx0 is an inflection point, a small balcony. One goes up and continues going up after that point, or one goes down and continues going down after that point. And note that at an inflection point, one can have also the first derivative different from 0 as well, as I said. Because, I mean, it's not necessary at an inflection point that the first derivative be 0. But it can be 0 as well. You see? All right. So, let's see also, let's check these on these curves, on these graphs, and understand what an inflection point is a little bit further. So each relative local extremum must be a stationary point, but not every stationary point needs to be an extremum. Why? Because it can be an inflection point as well. Or the first derivative can be 0 there by chance. There can be a small balcony, some point where the first derivative is 0 by chance. It's not necessary to be an extremum or a minimum or a maximum. All right. Here we see, you see the same picture as before, the same graph as before. We have B and E, which are relative maxima, C and G, which are relative minima, and D and F, points D and F, which are inflection points. So let's see this first derivative test just visually on this graph. First, we have the absolute minimum, which is A, and the absolute maximum, which is H, these points. We are not interested in them. We are interested in local minima, maxima, and inflection points. So, from A, we go to B. How do we go? We climb uphill. We go upwards. How do we know it? The first derivative before the point x0 here, before the point B, is positive. We go upwards. At the very point x0 here, at the very point B, the first derivative is 0. The tangent line is parallel to the x line, to x-axis. The x-axis. It becomes horizontal. The movement stops for one moment there. And then, when we pass to the other side of this B, of this critical point, where the first derivative is 0, the derivative becomes negative. We are going down now. So we have climbed the hill, we have gone up the hill, stayed stood for just one moment there at B, and then started to go down again afterwards. So this is the top of a hill. This is a relative or local maximum. No doubt about it. All right. Then we continue going down. At C, at the point C, the first derivative becomes 0 again. Here the first derivative is negative before C. Here, at this region, before B and C. It is negative. We are going downwards. At C, it becomes the first derivative becomes 0. We just stop for one moment. And then at the other side of the x0 here, of the point C, the first derivative becomes positive. So we are climbing again. We are going up again. What does it mean? We go first down, stop, and go up. So this is the bottom of a valley. No doubt about it. It's a relative or local minimum. Then we climb up. We go up to the point D. Here again, the first derivative is 0. We have climbed up to here. We have gone up to here. And then after that point, we go up again. The first derivative is positive here as well. At both points, the first derivative is positive. It is 0 by chance at this point, D point only, at the point D. So the point D is an inflection point, not the crest of a hill, not the top of a hill or a bottom of a valley. It is just a balcony, small balcony. It is an inflection point. Then we climb up to the point E. We go up. At the E, the first derivative becomes 0 again. And then at the other side of E, the first derivative becomes negative. We are going down. So we go up, stay and stand still and for one moment, and then go down. So this is the top of a hill again. And then we go down up to the point F, stand still for a moment, and continue going down again. At both sides of the point F, the first derivative has sign negative. It doesn't change sign. So this is a small balcony. This is a inflection point. Then we go down up to G. The first derivative is negative. At G, it becomes 0. This movement stops for a moment. And then it goes up again. The first derivative becomes positive. So this is the bottom of a valley. It is a relative or local minimum. You see that we can understand, we can analyze, and we can see, even if we don't draw this graph. In fact, nobody gives us this graph. We should draw it from our knowledge of analysis. Then we know that B and E are local maxima, top of hills. C and G are local minima, relative minima, bottom of valleys, and D and F are inflection points, small balconies. Well, at an inflection point, here we see an inflection point. Here at the graph A, at the point x equals G, we have an inflection point. Here the first derivative is 0. At before and after J, the first derivative is positive. You climb and continue climbing. You go up and continue going up. And it is the same thing here at the graph B. The difference is that both are inflection points, and when you see the derivative of this function, those are the primitive functions. When you take the derivative of this function, here you obtain positive, it becomes 0, and it becomes positive again. So it makes this curve. This function is probably a third degree polynomial, x cubed, a cubic polynomial, and its derivative is a square, it's a parabola, second order polynomial. So it is positive everywhere, but but at 0, it is positive, but it goes down. It goes from positive to 0 and then becomes positive again. It makes this thing. Here, it's it is positive in both sides as well. You climb and continue climbing, but the first derivative is not 0, it is positive. So you have a tangent line whose slope is positive but going up, reaches a maximum, a steepest sort of ascent, the steepest first derivative, tangent line, and then it is still positive, but it goes down. It becomes less positive. So it makes this curve the first derivative. So you see, this is an inflection point as well. And at an inflection point, we don't have to have the first derivative 0 always. All right. The second derivative will be 0, as we will learn afterwards. So let's see some examples. The first example is y equals fx equals x to the power 3 minus 12x squared plus 36x plus 8. The problem is finding the stationary critical points and see and analyze what they are, whether they are local minima or maxima or inflection points. So what shall we do? We will take the first derivative. F prime x is it's a polynomial. You use the usual rule to take the derivative. You just put the power in front and reduce the power by 1. So 3x squared minus 24x plus 36 plus 0, which is 3x squared minus 24x plus 36. This is the first derivative. We equate this to 0 and solve this equation to find the critical points. All right. This is the first order condition, which gives us candidates, but it doesn't say us what they are. Second order condition will give us the nature of these critical points. It will say us what they are. It will tell us what they are. So 3x squared minus 24x plus 36 equals to 0. Great. I can simplify it by 3, and I can divide both parts by 3 and obtain x squared minus 8x plus 12 equals 0. And factorizing it, if you can see the factors, you can factorize it already. If not, you can take the delta, the discriminant method, and find the roots. It's the same. But it is very simple here. We see that it is x minus 2 times x minus 6. X minus 2 times x minus 6. So x squared minus 2x minus 6 is minus 8x. And minus 2 times minus 6 is 12 plus 12. So those are the factors. X minus 2 times x minus 6. And this is equal to 0. If the product is equal to 0, or each of the factors should be equal to 0. So x minus 2 is equal to 0, or x minus 6 is equal to 0. If x minus 2 is equal to 0, from there we obtain the first critical point, x1 star, which is 2. And from the second one, x minus 6 is equals to 0, we obtain the second critical point, which is x2 star, which is 6. We can also put them in the function, in the primitive function, and obtain their y values, y1 star, y2 star. So you just put, when you put 0, it is obvious, you obtain 8. y1 star is 0, I mean 8. When you put 0 in here, and y2 star is 40. When you put 2 here, you obtain 40. But this is not so important. We have to make an analysis using the first derivative. So the first derivative of the function is 3x squared minus 24x plus 36, which is 3 times x minus 2 times x minus 6. You see? If x is less than 2, you can make a small table and see at which part it is negative, at which part is positive. When x is less than 2, x minus 2 is negative and x minus 6 is negative. So negative times negative is positive. So the first derivative is positive when x is less than 2. Between 2 and 6, when x is greater than 2 and less than 6, x is greater than, when x is equal to 2, it is 0. When x is equal to 6, it is 0 again. The first derivative is 0. Between 2 and 6, x minus 2 is positive, x minus 6 is negative. So negative times positive, or positive times negative is negative. So the first derivative is negative between these roots, 2 and 6. And when it is x is greater than 6, then both x minus 2 and x minus 6 are positive. The product and times 3 as well is positive. So we have positive, negative, positive. You see, it makes this movement. Positive, negative, positive, the first derivative. What does it mean? Before 2, the first derivative is positive. We are climbing uphill. We are going upwards. At x star equals 2 or x0 equals 2, as you wish, the first derivative is 0. The movement stops for a moment. The tangent line is parallel to x-axis. Then, when we pass 2, between 2 and 6, the first derivative is negative. We are going downhill. So the first point, the x1 star equals 2, which has also a coordinate of 4, we have, yes, we have 2 points, 2 and 6. The when you put in the primitive function, for 2 you obtain 8, and for 6 you obtain 8. So the first one is the maximum, the second one is the minimum. But anyway, we know it from the first derivative test. Before 2, the first derivative is positive, it becomes 0 at 2, and it becomes negative after 2, between 2 and 6. So you see, we first go up to the point 2 and then go down on the function. So 240, this point 240 is, whose x coordinate is 2 and y coordinate is 40, is, well, a local maximum. It is the top of the hill. Then we go down. Here at 4 we have also an inflection point, but since the first derivative is not 0, the slope is not 0 there. This test doesn't catch this point. This is the point where the second derivative is 0, as we will learn. But then we go down up to the point 6, x equals 6, and here again the first derivative becomes 0. Before 6 it was negative, and after 6 it becomes positive again. So we go down and up afterwards. What is it? It's the bottom of a valley. It is a local or relative minimum. So we know that which one is maximum, which one is minimum. This is the first derivative test. We can also do it with some simpler function, with an economic one, AC, average cost function, which is FQ, which is equal to Q squared minus 5Q plus 8. It's a parabola. A parabola with the coefficient of the higher term, 1, highest term, 1, positive, which means a parabola whose arms look upwards. So it has a minimum. It is making a U shape, so it has a minimum. We can already tell it. But say it anyway. We take the first derivative, and the first derivative is 2q minus 5. When we equate it to 0, we obtain q star equals 5 over 2 by simple algebra. Q star is equal to 5 over 2. We can also put here this 5 over 2 and obtain f of q star as 7 over 4. Great. It's a simple thing. Just replace q with f over 5 over 2 and calculate what is AC, f of q star. It is 7 over 4. Great. But it's not so important. So when x is less than 5 over 2, 2q minus 5, which is the first derivative of this function, is negative. If x is greater than 5 over 2, 2q minus 5 will be positive. So before q star, which is 5 over 2, when x is, or q is quantity produced or sold, is less than 5 over 2, 2.5, the first derivative is positive, negative. And after, when the quantity produced or sold is greater than 5 over 2, which is 2.5 or 2.5, whatever, 2.5, then the first derivative is positive. So we first go down and then up. So this point, the very point Q star, FQ star, 5 over 2, 7 over 4, this point is a local minimum, relative or local minimum, the bottom of a valley. You see? But it is also a global minimum. Why? Just think about it. It is because from the U shape of the function. So this is all for today. It's a short lesson for today. Anyway, we have covered 9.1 and 9.2. Then we will continue with 9.3, 9.4, whatever. And here you have the exercise for 9.2. You have from the third publishing and fourth publishing of the book. They are more or less the same, but there are some small differences. Just perform them all. Look at the back of our book. There are some solutions, but most well, all the solutions are in the solution book as well, which I shared with you. So you just first try them first, and then look at the solutions and work for yourself. If you don't understand something, you can always reach me from my phone, cell phone, or WhatsApp, or whatever, email, whatever you wish. So thanks for today, and have a good luck. Study well, and have good results at the final. It is approaching. Thank you very much, and this is all for today. I am stopping the recording.